The next speaker is Angelika Humbert. Angelika is the head of the section of glaciology at Alfred Wegener Institute in Germany, which is one of the largest institutions in Europe, I would say, dealing with polar science. And as we have seen, I mean, Antarctica and Greenland are melting. Especially Greenland is melting from the top, is melting from the bottom. And the ocean play a key role in this process. And what we see is a new insight on Greenland ice sheet and losing mass forced by the ocean. Thank you, Angelika.
Thank you, Carlo. Thank you for the invitation. And I'd like to present you now how the ocean is acting on the Greenland ice sheet and what's the mechanics behind, because that's my perspective. So if you look at the Greenland ice sheet is sitting, it has different kinds of ocean currents just everywhere around the Greenland ice sheet. And the basic action that the ocean does to it is you always have around the margin of the continental shelf, you have eddies. And these eddies are carrying heat. And by turning over, these eddies are able to transport the heat onto the shelf. And onto the shelf, this warm ocean water is able to meet the face of the glaciers. And I'm going to talk about how that works, how the feedback to the glaciers are. And as Connie already showed before, the ice sheet is losing mass. So what you first do is you investigate how much mass and volume is the ice sheet losing and where does it lose the mass in order to estimate which kind of processes are behind that. So if you look at the systems, so Greenland consists of two different types of glaciers. You either have a glacier that has a kind of floating tongue when it meets the ocean. So the ice starts to get afloat wherever it meets the ocean, and that's what we call a grounding line. And what you see here is a tidewater glacier with a floating tongue. And this floating tongue is moving up and down with the tides once or twice a day. So you have a hinge zone, like you would have a hinge if you are bending a paper or if you're bending any type of plate. And it looks a bit different in summer months. And you have these meltwater lakes on top, and you have the drainage of this surface water to the base. And a different system is these tidewater glaciers, where you actually have a calving front that's sitting directly into the ocean, and you have a calving of icebergs every hours, every day, so small pieces of ice. And then in addition, you have these larger chunks of ice which are calving off, and that's what you could also see in the movies that you have seen in the exhibition at Geochi. Okay, so how do you measure the surface elevation change over time? We use satellite imagery for that and satellite altimetry. You can use both. You can use DEMs, digital elevation models, and the change of these digital elevation models. And what you need to have a repeat visit of the satellite. So the basic idea behind that is that you have a satellite that's sending out a pulse. It might be a radar pulse, it might be a laser pulse, and you're measuring the time it takes this pulse to get back to the satellite. Then this satellite is going around the globe in orbits, and it has a repeat visit time, like for example for Cryosat 2, it's 366 days, and in that time you do have a change of the elevation. And what you do is you estimate the elevation change over time, and then you have to interpolate this over the entire ice sheet. So you do not have a spacing every meter, you have several kilometers in between these tracks, and then you estimate along the tracks the change in the elevation, and then you are interpolating this over the entire ice sheet. And that's an example of an average from 2011 to 2014. So Cryosat was launched end of 2010. So I always show you 3-year cycles because there is a large variety in between the years, and it makes much sense to make a kind of average over 3 years, and then you estimate the amount of volume change over that time, and every reddish color shows you how the surface lowered, every bluish color how the surface has growing. So that's 2011 to 2014, 12 to 15, 13 to 16, and 14 to 17. And I go back and forth a bit. So you see there is a variability in between the years. So that was a time frame which was very strongly pronounced elevation loss in the western areas and mostly all around the parts. But you also see that you have times where the elevation is changing in the positive direction. So you do have a large interannual variability, and this interannual variability is coming from surface melt, as Conny Steffen showed you. But there is a pattern that you see which is not connected to surface melt, and that's coming from the acceleration of glaciers. Because this acceleration is something that takes for longer. You start to accelerate a glacier due to a physical mechanism at its grounding line, for example, and then this material has a certain response time. If you change the atmosphere or the ocean temperature immediately back to colder scenarios, the glacier is still accelerating because it cannot sustain this very short time changes in the climate system. But if you look at the Greenland ice sheet and look at how much the elevation change has changed to another system, satellite system, to ISAT-2, for example, between 2003 and 2009, so you can estimate this elevation change for these two time periods and compare to each other. And that's really drastic, because if you look at the elevation change over the years in these in this time period from 2003 to 2009 and 11 to 14, you see that you have a very pronounced area in the southwest, which is due to the acceleration of glaciers like the Jakobshavn-Isbrae, and it started to come further to the northeast. So that's a change in the whole pattern. Yeah, you now have the pattern already with elevation change in the northeast. So if you look at the numbers, you might want to look at the topmost line here, which shows Greenland. So you had a volume change of 146 in 2003 to 2009, and you are now up to 375. So this is really a drastic change in between these two time periods. And this shows that the mass loss of the Greenland ice sheet is accelerating. It's not only a linear trend, it is really a non-linear trend. So what's important for us is that also in future we need to have this capability of satellite techniques to have continuous missions that we can go on with these observations to 22 to 25 to 2030. So that's important to have a continuous mission giving you this data. And as was already shown before, this is causing sea level to rise. And you see here in the left graph from the University of Colorado, the sea level curve that's coming out monthly, basically. It's also the same technique, it's also altimetry, and you see the trend. And it's 3.4 millimeter per year right now. When I gave my first talk and showed a sea level trend curve, it was still 3.1. So that's really a change over just a few years. And of course, this is only showing you the global mean sea level. But you living in Venice, for example, global mean sea level does not mean anything to you. You want to know the regional sea level. And the regional sea level trends are the trends that are affecting the societies. If you are living in a mega city, if you are living at the North Sea coast, the regional sea level trend is a key issue. And that's not only a volume change. It is an interaction between this mass loss you have from the ice sheets and the interaction with the ocean. So you do have also this heat uptake from the ocean, but it makes quite a difference in at what location the Greenland ice sheet is losing mass, in how much the sea level rises, let's say in London, let's say in Venice, or at the North Sea coast, or at the small islands. So this distribution of the ice loss around Greenland is determining your regional sea level. This is one part, a kind of feedback via the gravity. It's called self-gravitation effect. You have the large mass of the Greenland ice sheet, which attracts the large mass of the ocean. if this large mass of the ice sheet is getting smaller, then the attraction is lower. Your sea level around the Greenland ice sheet is dropping, but this volume has to go elsewhere. So it's going to other areas, and that is making a fingerprint, so the distribution of the regional sea level. And I think I don't say much about the figure to the right because it has been shown. I think Andrea Tilche was much more optimistic than I am. I don't see really a change over time. I just see the curve continuously rising, and I also hope that we will have a plateau. So coming back to Greenland, if you look at the left graph, this is a projection of how the Greenland ice sheet will change over time, and both graphs are taken from the IPCC report. So these contributions are contributions both due to the surface melt of the Greenland ice sheet and how the atmosphere affects the surface melt, but also due to the acceleration of glaciers. And if you look at the scale here to the right, this is a low scenario. We are now at 406 ppm last month, I think, CO2. So we almost made it to this scenario. And you see in green color, in dark green color actually, the contribution of Greenland. And this is up to 2,500. So I would say this is something we have more or less already committed to, but you also have these kind of contributions like 500 to 700 ppm, and here the scale is going to 1-2 meters. So this is an estimate. This is based on ice sheet models, and models are of course not perfect, and I want to continue with a few comments on what models do and what models can't do, and what kind of questions we typically face also as modelers from the society. So one statement I often hear, where do all these scientists want to know that from? The other thing is, just in the recent past, Andrea showed that very nicely, it's this kind of doubt. The belief in science is highly overrated. And if you look at the other scientists, engineers, or things like, they are also a bit, what do these models really contain? What could they do? What are they not capable of? Every model is only as good as the processes, the physical processes that are included are described. Of course, how else could it be? The other thing is we need input data, like the bedrock topography, for example. We need basal melt data, for example. And our models are only as good as the input data is, that's for sure. So what does this modeling mean? What do we really do? At the very beginning, you have an understanding of the physical system. You have the ice sheet there, you have the material ice, you need to find a physical description of that system. In our case, it is continuum mechanics. So we describe the material and the system not on the atomic scale, and we don't do it like an engineer would do it constructing a bridge. We are in the intermediate part. We want to describe the deformation, so the change in the shape of the material, because that is what's happening if you have a glacier that is flowing and moving. It is deforming. And this deformation is described by typically, in our case, creep, because the material ice is creeping. And what you could do is you could find mathematical models, so you have a system of equations that you later on need to solve with a computer. So you need to discretize these equations, and then you put them onto a grid and solve these equations with a computer, because there is no analytical solution to these equations. So what is in these models? The one part of the models is what we call balance equations, and it's very similar to balance equations that you use in many different engineering approaches. So for example, if you have a company which is producing chocolate and you want to compute how your liquid chocolate moves in your pipes, this is the same type of equations. It's also the same type of equations that you use to estimate how long a bridge would sustain if it's made of concrete. So you have balance equations for mass, for momentum, and for energy or enthalpy. And this is actually only the system that's described. It's not yet the material. So you need to close this equation system with a material description. That's what we call the constitutive equations. So you describe then the material ice and its behavior, how it deforms. And this is in our case a rheology which is describing a viscous flow, because the material ice consists of many small grains that are deforming, and it is a very viscous material, and it has certain properties. It's softer if it's warmer, and as faster you are deforming it, as softer it gets. It's a little bit like ketchup. You are shaking a bottle of ketchup in order to make it more liquid. And that's the same type of behaviors that you find in ice. And then the most important thing is at the last, you are having boundary conditions for the system. And that's the atmosphere at the top of the ice sheet, that's the ocean temperature at the base of the floating tongues or the faces of the tidewater glaciers. So that's what we typically do if we model ice sheet behavior. And as an example, I show you how the Jakobshavn Isbrae, which was also shown already by Connie Steffen, and where you have this nice movie in the exhibition, how that has changed over time and which process has done that. So this is the calving front of Jakobshavn Isbrae in colors the different years. And if you look at the system, so that's a kind of broader picture. It's you have here the fjord in which the glacier fronts are sitting here. This is the main trunk of the Jakobshavn Isbrae. And if you take a few dots here and look at the velocity of the glacier at these locations, and you do that over time, then you do see a speed up of the glacier. So this is most downstream, so a location where the calving front was. So you do have a cycle which is a seasonal cycle. It's always flowing faster in summer because the calving in summer is higher, and it's as further upstream you go, as less pronounced is this acceleration and as less pronounced is the seasonal cycle. So that's a typical behavior, and what you can see is that this glacier has accelerated tremendously here, and its maximum speed was reached just at about 2012, 2013. So if you take a model and try to model the flow velocity of this glacier, then you set up a three-dimensional model of the entire drainage basin, and you solve all these equations that I have explained to you, and I show you now along this black line just a cross-section of that. This is going over time, so the color is denoting the temperature, and you see the volume change and where the location of this grounding line, so the transition to the floating part is. You see how that point is also moving over time. So the calving front is going back and forth and back and forth. That's the forcing of the glacier. And you see how the glacier responds. Now it starts to retreat quite quickly. And this is because it was reaching here a location where the bed has a retrograde shape, meaning that the gradient of the surface topography is pointing inland. And it's very easy to retreat a glacier in this situation. So that's what the model shows you, and if you compare that to the observed data, and these are again these kind of seasonal changes in the velocity over time, you see in the lines that's what the model gives you, and in the dots what the observation is. You see it's not too bad. It's surprisingly good actually. So the effect of the change in calving rate, that's a large part of the acceleration of the glacier, and that change is also driven by the ocean. And how is that driven by the ocean? So if you look at the front of a tidewater glacier like Jakobshavn Isbrae, you have this amount of the calving phase which is below sea level. And if you have in front of the continental shelf a warm water mass, it needs to go over the continental shelf, which is often done via this eddy transport, and it needs to reach the glacier face. So it starts to melt at the glacier face, and with melting the glacier face, you have more bending stresses on top, and it can easier calve off, so the calving rates are going up. But for the warm water mass, it's not always so simple to reach the glacier front, because often you have what the oceanographers are calling sill. So you have a surface topography which needs to be kind of stepped over from the warm water masses. And due to the changes in the circulation, in the wind patterns, these warm water masses are now pushed over the sill, and you can measure that the temperatures in the ocean are getting higher, and you can see the changes in the calving rates. So you do have a kind of circulation, overturning of warm water then here at the top, and this is what also the satellites can observe. So this is a basic mechanism. So you have two chances of the ocean to act to the glacier. One thing is if you have these floating tongues, you can start to increase the basal melt from below, or you can increase the calving rates, and both are affecting the glaciers tremendously. Because you need to think of these floating tongues as a kind of, they can give some buttressing effect to the inland ice glacier. So they are holding back this mass. If these floating tongues are getting thinner or smaller in area, in that case this buttressing effect is reduced. So the glaciers can easily accelerate because they do not have this force which is pushing them back anymore. So losing the tongue was a key issue for the Jakobshavn Isbrae. It lost its tongue in 2003, and subsequently it started to accelerate. So this change in area of this floating part is really of tremendous effect for the glacier itself. So if you think, okay, we have understood what's happening here at Jakobshavn Isbrae, so what you would expect to be the next step? What could happen next? Side, of course, the surface melting. So the next area one would want to look at is the northeast. And due to one reason, it is because you see already an elevation change in the northeast, and that makes it suspect to understand what kind of mechanism is behind that. And the other reason is that if you look at the flow velocities of the Greenland ice sheet, you see in reddish colors here and in greenish colors, you see the glaciers which are flowing fast. And you see these only large ice stream in Greenland, which is called Northeast Greenland Ice Stream. This area is draining about 8% of the entire Greenland ice sheet. Knowing that the Greenland ice sheet has quite a volume for contributing to sea level change, a large system like this Northeast Greenland ice stream is of course important to monitor. So if you look further, then you could take a look into the projections of the surface temperatures, and all those projections are not including very good ice models. But still, if you look at those, if you look at RCP 2.6, which is likely below 1.5 degrees, or RCP 4.5, which is more likely than not to be below 2 degrees, and you take a look at Greenland here, you see that in all cases and in all times, so 2030 and 2090, it is Northeast Greenland which is facing most of the warming signal. So this is the area where the large change in future is to be expected. And these projections, if you look at different models doing the projection, all of them are telling basically the same story. It's the Northeast Greenland sector which is facing the warming in future. So what to do if you want to study the system? One of the outlet glaciers of this Northeast Greenland ice stream is the 79 North Glacier, and one is the Zacharias Isbrae. The Zacharias Isbrae, it's not a very nice map, I have to be honest. This is a glacier which has retreated already in the past few years, and you see a lot of icebergs. I show you a photo at the end. So this one is retreating and accelerating already quite a bit. This one here, the 79 North Glacier, that is the outlet glacier draining one part of the Northeast Greenland ice stream, and it has a floating tongue, which we call 79 North Glacier. So this is a floating part. So everything that's bluish here is moving with the tides up and down every once or twice a day. So if you want to understand how that glacier changed due to ocean forcing, you would want to understand how the circulation here works at all. And when I started to work together with oceanographers working in this area just a few years ago, I was surprised because they didn't know in which direction the circulation goes. And one of the hypotheses is that the warm water would come from this direction or from that direction, and then it makes its way underneath this glacier tongue, starts here at this area to melt the ice from the base, and by that cooling down, and then exiting at this direction. But there was a large question mark, is this really the direction the circulation goes? And just recently we understood that the way is different. So this is the route the water takes. So the warm water is coming here from the south. It's draining underneath a floating tongue on that side. It's transporting the heat to this transition line, the grounding line between the inland ice sheet and the floating part. And then it's cooling down and exiting the glacier on this side. So if you want to understand how this glacier is changing in future, you want to know how much basal melt, so melt at the lower side of this floating tongue is happening. And of course you also want to know how the geometry of the system looks like. Is it very kind of prone to change because it has a surface topography which is really sustaining a change? So if you take a cross-section along the glacier like this, then this is how it looks like. You do have this floating tongue, and this is a location of the grounding line, so the transition to the inland. And you do have a velocity of the glacier, so its flow speed. And this is also the location where the contribution to sea level change takes place. Because in the minute that the ice is already afloat, you don't have a contribution to sea level change anymore. So it is not the calving at this end which is the mass loss. The mass loss of the Greenland ice sheet due to discharge is taking place right at the transition from the inland to the floating part at the grounding line. So it's important to know how much ice is discharged, and for that you need to know the velocities at that location. So these velocities are not only determined by the deformation. I told you that ice is deforming like a viscous fluid. It is also the lubrication effect, and with that the sliding. So this block of ice is also sliding over the bedrock or the sediment underneath, and it makes quite a difference if you do have a warmer ice mass, so if your ice at the base is quite warm, or if you have in addition to that subglacial water either coming from the inland, or like Conny Steffen showed, that you have these supraglacial lakes that are draining. So if you have this drainage, you have an additional lubricating material, and the glacier can start to accelerate. And this is then this, together with the basal melt that I try to sketch here, the change that you are doing to the system. So what you would want to know is how much will an increasing basal melt change the velocity structure at that location, yeah? And for that you want to know the basal melt, of course, and you want to know how the geometry of the glacier in general looks like. And this is a radargram, more or less the same cross-section that I sketched before. And it might look confusing for a moment, but just to give you an orientation, this is downstream the glacier, so this is along the cross-section, and this is a vertical scale. And all glaciologists have a kind of gene defect because we are thinking here in kilometers and here in meters. So extend that by a factor of 1,000. And the data is a bit confusing, so I mask out two areas because this is below the ice base and this is above the ice surface. So don't look at these two areas, but look at the rest. You are seeing here in this very dark color the surface of the glacier, and you can see here the base of the glacier. And that's actually how we measure ice thickness. We are using ground penetrating radar and get the reflection from the base, and from that we know how the basal topography looks like. And from here on, from this location on, the glacier is afloat. So this is the floating tongue. It's back. Okay. Okay, so this is the floating the floating part on this side. So what you want to do is you want to measure the basal melt on this side, and you want to have also ocean models computing this basal melt and coupling that to ice models. Just to get back to this, what you also see here is that the base of the ice sheet is having again a retrograde shape, so it's easy for this glacier to retreat. Yeah, it's sustained in the way that it can be pushed quite easily backwards. So I jump over these two. So how do you measure basal melt? It's also a radar technique. You are measuring the base of the ice sheet or the floating part of the ice, and you do that over time. And as the change in thickness is so small, you cannot use the amplitude, but you measure the phase of the signal, and with that you can have a resolution of millimeters per year. So this is how you do that, and that's how it looks like. We just brought out last year a station at the grounding line of 79 North Glacier. So this is the electronics and the batteries, and that's the antennas. And when I saw yesterday these nice photos of these foxes, I mean, they are looking so scenic, but these animals are really a threat to our instruments because they like to bite into all these cables. So you don't have to only to protect your instruments against harsh weather, it's also the animals we have to protect them from. Okay, and besides that, you have these animals and the weather, it's also very crevassed. So this is the location of the grounding line up here. You do have a supraglacial lake. It's actually frozen. I took this picture in March. But what I want to show you, it's really harsh conditions because exactly where you want to know the basal melt rate, it's fully crevassed, and you have either the threat that you are losing your instrument or you can't land with a helicopter. So the whole system is acting against you as a glaciologist because it's quite difficult to work there. Despite that, we are going back this year in July and take out a larger field campaign in which we want to measure the basal melt rate across the entire floating tongue and set out more of these autonomous instruments in order to measure the velocities of the glacier and how that changes also over tidal cycles. So coming back to that, it's East Greenland, which where the heat is on. And coming to a conclusion, I think my next slide is already the conclusion. I'd like to show you one photo that I took last year in March at Zacharias Isbrae. And this is a very typical picture. And for all the photographers in the room, this is a poor photography for sure. But what you see hundreds of icebergs. And when I saw yesterday in the exhibition these scenic photos of icebergs, it is a kind of twofold emotion you have, because the carving of an iceberg is a very normal thing. Forever, glaciers have carved off icebergs because that's how they are losing mass. And losing mass, like a tree is having to lose its leaves in autumn and is getting new leaves in summer. So this is a kind of cycle. So if you have glaciers carving off icebergs, that's a normal thing. But if you have massive expel of icebergs, like you had when Jakobshavn Isbrae was losing its floating tongue, or what you see here with Zacharias Isbrae, you have hundreds of icebergs in a bay, and that is a signature of a glacier that had a collapse of its floating tongue. And if you fly over Greenland, you can not only see that with satellite data or with instruments on the ground, you can see that visually with your own eyes. So that's a typical sign for a retreat and a disintegration of a floating tongue. So it's a take-home message in short. There is more than enough evidence that the ice sheets are changing and in a rate that is affecting our society. There is no doubt about that. If you look at what does that mean to those who are taking political decisions or who are taking decisions in industry for changing their way for emissions, for example, they all have to keep in mind that doing the decisions will now and in the next decades will always be a decision with uncertainty, because the ice models are still not incorporating all the effects. We can do projections, but the projections are having an uncertainty, for sure, and that will last. So the challenge of making decisions in future will always be this challenge of taking decisions despite having uncertainty. And for us as humans, that's simple. If you go to the forest and collect mushrooms, and you have a basket full of mushrooms, and you know one is deadly poisoning, you won't eat it. It's a very simple decision you are taking. But that's the same type of decision you have to take as a leader in order to change the pathway of the society. You always have to do a decision under uncertainty. And last but not least, it makes a tremendous difference in the projections in where the Greenland ice sheet is losing mass. So it's important that we are investigating more the processes and doing this by both doing observations, either in the field or with satellites. We need more theoretical studies, for example, for sliding. Sliding is a very poorly described process. And we need to improve our models, that's for sure. So that's my take-home message. There is the evidence. It's always a decision that is taken under uncertainty, and the understanding of processes needs to be improved. Thank you.
Thank you, Angelica. We have time for one quick question.
Good morning. I was thinking about the causes of the rising temperature. Of course, the main problem is the industry based on fossil fuels, but I was wondering about the way in which we feed ourselves. Cattle raising is very known for producing a great amount of methane that contributes to increase the level of greenhouse gases. So do you think that meat consumption, especially beef consumption, has a great influence on global warming? Thank you.
For me, it's a difficult question to answer because I'm a glaciologist. I can tell you how the ice sheet behaves, so under a certain boundary conditions. So I think you need to pose these type of questions to different type of scientists, those who are doing atmospheric research, because it's also a kind of chain that we have. Glaciologists can tell you how ice sheets are behaving under stresses from outside, so atmosphere and ocean. But you need to pose these type of questions to atmospheric scientists, like Carlo, for example. So I hand that over to you.